All right, so I'll start recording here. A couple things. Make sure that in your chat, so everyone do this right now, please, set it in the to line to everybody. That'll help me, just because if you ask questions, I'll repeat it, but this will allow everyone to benefit from the questions that are being asked. I think that's it. I will be recording this session, as I already started recording it, but I will be posting it on my YouTube channel. So for those of you who have friends who can't make it tonight and still want to benefit from this session, they can watch it on my YouTube channel, and that will also have linked the things, just like every other semester. All right, so let's get started. Let's crack one for the chemists who can't be here right now. All right, it's a LaCroix. All right, okay, so this will give me the energy to get through this these 2 hours. All right, okay, so can we throw up in the chat where we want to start? Oh geez, okay, people are prepared. New material. Okay, so those look like questions. Okay, so we'll just work through the new material. All right, everyone has the key. So, and make sure if I make mistakes, because I'm working through this pretty quickly, please point out my mistakes. All right. Okay, let's get started. Oh, actually, before we do that, make sure you have your calculator. Hopefully you have access to the supplemental information that will be given at the exam, the final exam. So make sure you have that, so you know what you can reference to, when you're on the exam. All right, and your periodic table. Make sure you have your handy dandy periodic table with you. All right, so we'll just start through new material. All right, so new material that hasn't been covered on a midterm yet. Oh, actually, before I begin, I wanted to tell you that I am beaming up to your frontal lobes via Starlink. I just got Starlink yesterday. All right, so for those of you in my class, you know that I live on a farm, and basically my internet for the past 2 years has been a cell phone strapped to my roof. All right, actually it's this antenna that's pointing out my window. That's what my internet was before, but now I have Starlink, and it's so great. Through the power of low orbit satellites, I have reliable internet. This is what it looks like. Oh, whoops. No, here, I'll show you a picture. See, that's what Starlink looks like. Those are my chickens. Okay, it's just like a dish. See right there. My husband's mowing the grass right now. I took this before coming out. So there, that's my little story. Okay, sorry, let's go back to gases. All right, chapters 10 through 12, we haven't covered on a midterm yet, and I'll just point out, I think questions have been asked, is the final exam mostly going to be questions on chapters 10 through 12? I think all of these chapters are represented evenly. For the final exam, there are 53 questions on the final. So just anticipate every chapter being represented equally. So that means there's going to be about maybe 4 questions per chapter. So 4 questions for chapters 10, 11, 12. So that would be a lot smaller than a typical midterm, if it was just a midterm on 10, 11, 12. So keep that in mind. I wouldn't consider it less material for 10, 11, 12. Everything's just represented evenly. Okay, all right. So question 1, we have a high altitude balloon. And it's filled with some volume of gas of helium at this temperature and pressure. What is its volume when the balloon goes 200 kilometers in the air? So probably a little less than low orbit, where Elon Musk's low orbit satellites are, but it's at a lower temperature of negative 48 degrees Celsius and a lower pressure, 63.1 torr. So within gases, we learned basically 2 different equations. And I think it's sometimes, it's a fair question, like when do I use the combined gas law versus using the ideal gas law? So here's the combined gas law. The ideal gas law we know is piv-nert. And so the question is, when do I use this? When do I use this equation? They're actually both the same equation, but my idea is I use the combined gas law when we have a sample, one sample of gas, and we're changing its conditions. We're changing its, temperature, changing its pressure or something. And we want to understand how does that sample change to keep, these quantities, these ratios equal to one another, versus we use the ideal gas law when we're just looking at one sample given some type of conditions, and we want to calculate moles of gas that are present. So question one, I clearly see, the sample's changing. We have one sample of gas and it's changing conditions. So right off the bat, I know to use the combined gas law here. Within the combined gas law, we have our named gas laws within there. So like Boyle's law, Charles, it's just if one of the quantities stays constant, it falls out of the equation, because essentially you have the same value on the same side of the equation, and how mathematics works, they just cancel out. So in question one, everything is changing. I like to identify all the values given. So the volume here, I'm going to call that V1, meaning it's the volume at state 1, and it's at this temperature and this pressure, and it's changing. And we actually want to figure out, okay, what is its new volume given these new conditions, T2 and P2. So the idea here when using the combined gas law, it doesn't matter what units the pressures or volumes are in, as long as they match. But the one caveat here is that temperature needs to be in the unit of Kelvin. So we'll have to convert those temperatures to Kelvin. And if we look at the pressures, they're different. So we just need to convert one of them so they match. And then it's just plug and chug at that point. So filling all of this in, 1.41 times 10 to the 4 liters. All right, that's V1. P1 is 1.01 ATM. I'll convert the torr value to ATM here. And then T1 is 21, but this needs to be in Kelvin. All right, so do not forget that step, 273. And that would be in Kelvin, equals P2, which is 63.1 torr. Let's convert that to ATM, so divided by 760 torr. Are you given pressure conversions? Can someone tell me? Is that on the sheet? Are pressure conversions there? No, okay, all right, so do memorize these. 1 ATM equals 760 torr. Also, that's the same unit as millimeters of mercury, 760 millimeters of mercury. What other ones are there? Probably PSI, 14.7 PSI. And maybe if you have room in your brain within Pascal units, which is our SI unit of pressure, is 101.325 Pascal. So those are some that you have to remember within there. So there's really only 3, I guess, since millimeter of mercury and torr are the same. All right. Okay. So there's our pressure. And then our new volume, that's what we're calculating, and over T2. So negative 47 plus 273. All right, multiply all these things together, multiply by the temperature, divide by this pressure unit, and you should get volume. We can also, for fun, why don't we predict, will the V2 go up or down based upon some of our gas laws here? So if we kind of just track the values individually, temperature. So think about, how does volume and temperature relate to one another within gas laws? I think that's Charles' law. So it looks like temperature is going down. All right, so temperature is going down, and so if we think about temperature going down, how does volume change? Typically, when temperature goes down, volume decreases. That's why when we put a balloon in liquid nitrogen, it shrinks. The gas isn't going away; it's not going away. It's just the molecules aren't moving as fast in your container, so the volume shrinks within there. So based upon the temperature, the volume would go down. But if then we look at pressure here, pressure is also going down. It's going from, about 760 torr to 63 torr. Pressure is going down. The volume of the balloon should get bigger. So actually what I wanted to showcase here, we actually can't really predict which direction it would go based upon those two pieces of information individually. We have to just put it into the equation, but do understand how those different gas laws change our values, how pressure, volume, temperature are all related to one another. In all of those gas laws, typically one of the terms stays constant here. And so since pressure is going way, way, way down, we will see the volume of our balloon go way up. This is essentially how weather balloons work. They are filled in not a huge volume on at sea level, but once they go up into the atmosphere, they get a lot bigger within the atmosphere. So I don't actually, where's my key? You have the answer. It's 1.31 times 10 to the 5. So it gets an order of magnitude bigger within there. And the unit of our answer is in liters because that's to match the volume given within there. And so looking at Sig Figs, remember, Sig Figs, you have to work with Sig Figs for the rest of your life, essentially, if you're in the sciences. A reasonable number of Sig Figs here would be 3 because volume has 3. All our pressures have 3 Sig Figs. Even our temperature, because we convert it to Kelvin, and remember our addition rules, 21 plus 273, those are values known out to the ones place. And if I add that, what is that? 294. 294 Kelvin has 3 Sig Figs, even though the temperature given only has 2, because we do addition here, there will be 3 Sig Figs. Okay, there we go. So this type of question should be a piece of cake. It's just plug and chug. Just make sure that your units match and spec those units within there. Okay, so question 2, gases are sold. This should say sold, sorry, in large cylinders for laboratory use. What pressure in atmospheres will be exerted by this much mass of oxygen gas when stored at 22 degrees Celsius, 40 at a 40-liter cylinder? So, okay, that's a temperature and there's a volume. And so looking at this question, I see that nothing's really changing. So we're not using the combined gas law. We're going to be using PivNert instead here because we want to calculate pressure. That's what it's asking for. In inspecting the pieces of information given, we are given volume and temperature. R is a constant. Are you given R on that thing? I should have printed it out, but I didn't. Are we given R? Somebody? Are we given R? Yes, we're given R. Perfect. But make sure that you use the correct R. So we'll go through that here. So really the only piece, okay, we are given both of them. Very good. So make sure you use the right one. So the only piece of information we're not directly given is N in this case, and know that N means moles of gas. We aren't given moles of gas. We're given a kilogram amount of gas, oxygen. So this will require us to use molar mass to get go from a mass amount to a mole amount. So there's just a tiny step before we can plug and chug within PivNert. So I see 2.5 kilograms of oxygen. And so do recognize that oxygen is one of our elements that exists as a diatomic molecule. There is no just oxygen atoms floating around in our atmosphere. It's O2 molecules. So do know that so we can use the correct molar mass. I'm going to convert this kilogram value to grams first, so then I can use molar mass of oxygen. So if you look at the periodic table, oxygen is like 16. Yes, it's 16.00. So O2 will be 32.00 grams is 1 mole. So you get that 2.5 kilograms is 78.12 moles of oxygen. gas. And so that is N that we will use. This would be rounded to 2 sig figs, but I'm not going to round just yet because I still need to do one more step. So I'll just keep a couple digits at the end there. So now it's plug and chug. Pressure, oh, actually, before I do that, make sure when you use PivNert, because the R that is given, I'm assuming is 0.08206. The unit is liter, ATM, mole, Kelvin. So since this is the R that's given to you, you need to make sure that your pressure is in ATM, your volume is in liters, and will always be in moles, and your temperature is in Kelvin. So again, when thinking about gases, we want to be in Kelvin temperatures. All right. Okay. So then 78.12 moles equals pressure. That's what we're calculating, 40 liters. So we don't have to convert that, thankfully, and 22 plus 273 to get that into Kelvin. And so we get our pressure. This should be a pretty high pressure. Our answer here is 47 ATM. All right. And this should have 2 sig figs because our N amount, our mole amount has 2 sig figs, even though liters has 3 here. We're limited by 2 in our amount of gas. Yeah. So there we go. So lots of units to expect within there. Okay. Am I getting? Is my computer, is my thing lagging? Do you see me writing? No. My internet connection is stable. Come on, Elon Musk. But can you hear me? Can you hear me? Yes. Okay, there we go. All right. So there we go. All right. Sorry about that. All right. So keep going. Very laggy. It's working now. Okay. Sorry about that. Okay. Keep going with gases. How do we know which equation to use? Watch the video. The replay once we get to it. Basically, if the sample changes, use the combined gas law. But since in number 2, they didn't change, then there was no change in like pressure, temperature, then we use PivNert. Okay, so question 3. Oh, I think it's my iPad is the laggy one. All right, so we have another sample of gas. So we have a vessel with an internal volume of 10 liters, and it contains these amounts of different gases this time. What is the pressure inside the vessel? So 3 is very similar to 2 in that we are going to be using PivNert again because the sample conditions aren't changing. We're given a volume and a temperature, and we want to calculate pressure in this case. So the idea again is, okay, we need to figure out how many moles of gas we need. And so what's really neat about gases is that it doesn't matter, as long as we're working in moles of gas, it doesn't matter the identity of the gas. PivNert will always work, but the problem is that we have 3 different samples here of all different identities of gas. So, and their gram amounts specifically. So we have to convert all of those gram amounts to mole amounts. And then if we add up the total number of moles of gas we have, we can then plug it in to PivNert. So the first step here is we need to convert all of these into mole amounts of the different components. And so using the appropriate molar masses of all of those, you should get that there's 0.10 moles of N2, 0.200 moles of H2, and argon has 2.00 moles. So the majority of this sample is argon. So our sample has, these are the particles that make up the sample. Oh my gosh, my iPad's so slow. And so each of these gases will exert a partial pressure. So there's a couple ways you can actually calculate this question or figure it out. We could go ahead and take these mole amounts and calculate just plug them into PivNert individually and then add up the total pressure. So we would calculate, okay, the partial pressure of N2, the partial pressure of H2, the partial pressure of argon, and then add it up. I'll add those up. So we would use PivNert here, PV equals nRT for all of those steps, and we would get the total pressure. The lazy way I would do it is I would just add up all of these mole amounts to get N total instead and use PivNert, and I would get the exact same answer. So that's pretty cool. And the idea here is that each of the components based upon their mole ratios or their mole fractions within the sample relate to the partial pressures that each of those gases exert. So do recall we can talk about gases in terms of partial pressures when we input them into PivNert. We can also think about, okay, what fraction of the sample is N2, for example. So to get mole fraction, you just take the number of moles of N2 that are in the sample and you divide by the total amount of gas within that sample. And you can get the mole fraction. So it's that this is the fancy looking X, but it's chi. That's supposed to mean mole ratio within there. You can calculate the mole ratio for any one of the components of this gas sample. So you'll see that the mole ratio of argon will be the largest because there's just the most number of moles. So really what mole ratio is, or sorry, mole fraction is the percent of your sample in moles of your different components. So this is just another PivNert question, so I'm not going to finish it. You have the key. All right, so we just plug in these numbers into PivNert. We have liters, we have temperature. Just make sure that that is in Kelvin. All right, so keep moving on. Okay, so number 4, other ways we can think about gases other than just using PivNert or the combined gas law. So is the number you get for N going to be your answer? Look at the question. And this is a very good practice to do on any examination of any class is reread the question and see what is that question asking. So maybe ask yourself here, what is N? N is the number of moles. Is this question asking for number of moles of sample? No, it's not. It's asking for a pressure, specifically the total pressure of the vessel. So we are actually going to report P total for this question. I just kind of did a side review of some other terms that we went over that we discussed in class about mole fraction of gases, because this question is very similar to question 2. Okay, so no, we don't report N, we report our P total. Okay, so question 4. I would consider more of an application of the ideal gas law within here. So what I mean by application is we're using the ideal gas law to calculate some other quantity, but we still have to use PivNert in some capacity. So here, this question is asking, okay, of these gases, okay, no, actually it says which of these following gases has this specific density? Oh, my key is wrong, sorry. My key is wrong. I misinterpreted the question. I thought it says which of these gases is the most dense at this temperature and pressure. So if you're reading the key for question 4, it's wrong because I misread it. Even though I wrote it, I don't know. So in question 4, let's just go through the whole thing. It is asking which of the following gases has a density of 2.104 grams per liter at this temperature and pressure. So I like to remind myself what density is. All right, so density. So basically what we're going to have to do is calculate the densities of all of these gases. And so to calculate the density of a gas, remind ourselves what density is. It's a gram amount over a liter amount. And that's kind of shown here by the unit of density grams per liter. But the trick is, how do we get gram of sample and a liter of our sample? So when using the application of the ideal gas law here with densities of gases, I have a cheat, kind of. It's not a cheat, but we have to make an assumption in order to solve this equation. We need to figure out or start with some quantity of gas to calculate what is the density of that gas. So I like to cheat and just assume that we have 1 mole of gas, and that will make our calculation a lot easier here. If we assume we have 1 mole of gas, we can figure out, all right, we're going to say N equals 1 mole of the specific gases. We can calculate the liter amount using Pivnert. All right, we just need to calculate volume. We're given pressure and we're given temperature. So we'll insert 1 mole into N instead. So what we're actually doing is calculating the molar volume of a gas at a certain temperature and pressure. So the question is, okay, well, where does the gram amount come from? Well, since we assumed we have 1 mole of gas, we can just use the molar mass of that identity of gas to get the numerator part. And so for this specific question, we have to do it for every single one of them and figure out, okay, which one is closest to 2.104 grams per liter within here. So we have to do it for all of them. But what's nice, is the key correct for 3? It should be. Did you plug it into Pivnert? If you plug the N amount to Pivnert and it's not 129, it might be wrong. So you tell me what pressure you get if you plug it into Pivnert. Oh, 5.6. Okay, it's 5.6. All right. So sorry about that. Sorry. Yes, it's 5.6. So, but the N amount is correct, right? If we go back to 3. Okay. All right. Yeah. So the N amount is correct. Yeah, if you just plug and chug and you get 5.3, I believe you, it's 5.3. I don't know. I make a lot of keys. I'm sorry of all the mistakes that are within here. Okay. Do we need to go back to 3? Is that clarified? Okay, the answer is 5.6. I will fix it before I post this key again. 5.6 ATM. That's embarrassing. All right. So okay, let's go back to 4. All right, so we're assuming 1 mole of gas for all of them. So it's nice. What I will do is calculate the molar volume, the liter amount for all of them. What's nice is that they'll all be the same because all of them have N equals 1, same pressure, same temperature. They'll all have the same denominator, but they'll have different numerators at the top because all of them, if you have 1 mole of gas, they have different weights. So let's calculate that molar volume here. So pressure is 1.31 liters. We are calculating volume. N is 1 mole, times R 0.08206 liter ATM mole Kelvin. I bet I used the 8.314. I bet that's probably what I did for number 3. It's probably what I did. And then 303 Kelvin. So that's nice. That's already in Kelvin. So I get that the volume of 1 mole of gas is, I hope this is correct, is, oh, I didn't even calculate it. Way to go. Way to go. Okay. 1 times 0.08206 times 303 divided by 1.31. So I get a volume of 18.98 liters. So all of these will have the same denominator of this, about 19 liters. But what will be different is the numerator part. So to get, I'll just do helium real quick. So if we do helium, the density of helium, and remember, we made the assumption that it's 1 mole of helium. We already know 1.13 liters. Oh yeah, sorry, this is ATM. ATM. There you go. All right, we're calculating for volume here. All right. Okay, so density of helium here It's a gram amount over the liter amount. We already calculated that the liter or volume amount is 18.98 liters. And so the gram amount just comes from the periodic table. We know that 1 mole of helium gas is 4.003 grams. So for helium, 4.003 divided by that number equals 0.21 something grams per liter. So helium is not what we're looking for. If we kind of look at all of these pieces of these different gases, we know that helium is going to have the least dense, the smallest density, and xenon is going to have the largest density because xenon is the heaviest of all of these elements here. And so 0.21 grams per liter, that is helium. Oh, I hope their answer is here. I wrote this question. I hope the answer is here. So helium is 0.21. So to calculate argon, we do the same thing, but we're just going to put the molar mass of argon here instead. So 39.95 divided by that same number, that volume number we just got. So 18.98 liters, grams. Oh, I might have written this question so you couldn't answer it. Oh no, so this is the answer. So this one is the answer. Okay, so 39.95. It's hard to write questions. That's why I'm wrong all the time. Because sometimes I think of the answer and I write a question to be that answer, but sometimes I don't do it right. So that's what it would be for argon. So argon would be the correct answer. So the answer that you see on the key is incorrect because I misinterpreted the question. But for fun, let's do xenon as well. So the whole idea here, again, volume is the same because we are making the assumption 1 mole of gas. So for xenon, we would just do the same thing, but use the molar mass of xenon. So 131.3 divided by 18.98 liters. And we would get a really dense gas, 18.95. So, or 998. There we go. So the density of xenon here is 6.9 grams per liter. So just for fun. So we see that xenon is the densest, but argon's our answer because this one is looking for the density, which one has a density of this one. So for me, I can't just look at this and be like, oh yeah, argon has that density. No way. I actually have to calculate it. And so whenever working with density of gases, this is the assumption that you need to start with. You have to start with some amount of gas, and it's easiest if you just assume you have 1 mole of gas. You can actually pick any number, any amount of some mole amount of gas. It's just easiest to work with 1 mole, all right? And so that's when working with density of gases. Okay, so there we go. There's that one. And so overview of this, you just look at the unit of density, grams per liter, get the volume amount from Pivnert, get your gram amount from the molar mass of that specific substance that's there. Okay, all right, so let's keep going. All right, do we want to do, okay, so let's do 5. So 5, again, gases. So we have oxygen that is generated by the decomposition of potassium chlorate given by this reaction. If 2 liters of oxygen at this temperature and pressure is collected, how many grams of ClO3 were consumed? So this question is stoichiometry, essentially. We are given, so if you remember, midterm, I guess 1, when we worked with chemical reactions and stoichiometry, the key is in order to use the coefficients in a balanced chemical equation, we need to be in the unit of moles of substance. That's no different here. It's just a little bit different. Since we're working with gases, we'll use a different method to get moles of oxygen. So in chapter 3, to get moles of oxygen, we would use the molar mass of oxygen when we are given grams, but we're given gas measurements here, a temperature, a pressure, a volume. So we will use PivNert to get moles of oxygen within there, and then we work it just like a stoichiometry question from chapter 3. It's just we kind of start off a little bit different here. So kind of if we draw out like a roadmap of what we're doing, let's see if I got this question right. Yeah, so my strategy here for this question is we are given a volume amount of O2. We need to get to a mole amount of O2. We'll use PivNert to get there because we're given temperature and pressure. Once we have a mole amount of oxygen, we want to go to the substance that the question's asking for. So this question is asking for potassium chlorate. So we will go to moles of KClO3, but we don't want to stop there. We want to know how many grams were consumed. So we get to grams of KClO3 using your molar mass of KClO3. And so the step right here where we go from oxygen to potassium chlorate, this is where we use stoichiometry. All right, so basically this part, this is chapter 3 stuff. You should know how to do that already. You have a mole amount of one thing, you go to the mole amount of another thing, use molar mass to get to where you want. The new step is using PivNert within here. And so we're given volume, pressure, and temperature. So we're just calculating for N specifically. So when we do that, let's plug in all those numbers. So 760 torr, that's 1 atm. Times volume, so 2 liters, equals N, that's what we're calculating for. R is that constant that we use, but I'm not going to write it out. And then 227 plus 273 within there. So if you calculate N, this is like question 2, where we're just calculating a mole amount of a gas. Same idea. The amount of O2 that we have in this sample is 0.08124 moles. So now we want to figure out, okay, how many moles of the starting material, your reactant, do you need to start with? So this mole amount of O2, just to finish it off, we use stoichiometry to get to moles of what we want. So within using stoichiometry, we see the ratios of the coefficients given in the chemical equation. So let's review of chapter 3. So 3 moles of O2, 1 mole of KClO3. And now to get to grams, we just use the molar mass of KClO3. And so just use the periodic table to add up all those different elements. And so we get 1 mole of KClO3 is what mass? 122.55 grams. And so we get about 5 grams of our reactant is needed to do it. I got a different answer. Okay, let's try it. Okay, maybe I'm wrong, guys. 0.08 is my mole amount, right? Okay, I'm just going to back up. Let's back up. 2 divided by R divided by 27 point or plus blah. Okay. No, my mole amount is right. Okay, divided by 3 times 122.55. Why am I wrong all the time? Everything is right except the answer. Yes, that's my life. Double check when you're out, please don't be like me and double check your calculator work. Calculators are dumb. Okay. And so they're only as smart as their users. Okay. And I guess for me, the user is not very smart. So yeah, it's not 5, it's 3.3. Let's look at Sig Figs. A reasonable amount of Sig Figs would be 760 torr. I think that actually only has 2 Sig Figs. So I think our answer should actually only have 2 Sig Figs. We'll be much more clear within that. So 3.3 grams would be our answer. Okay, sorry about that. 3.36. Okay, yours is just a little bit off, or maybe mine's a little bit off. It's probably a rounding error within there. Okay, all right, sorry about all the mistakes. Okay, let me circle this so I can fix these answers before I post it tonight. When are other people's exams? I know that my students have their exam on Friday. Do you guys have exams other days? The other people that are here? It's Monday. Is there one sig fig because of moles? No, the mole amount should have 2 sig figs. So I was just lazy and wrote 1 ATM. Okay, but we want to look at the original question. So don't trust what I write. It actually should have 2 sig figs, because this torr amount, this really should say 1.0, has 2 sig figs, and liters has 3. Temperature also has 3 sig figs because of the thing. Tomorrow, well, I'm glad that you could make it to this. Doesn't the equation need to be, it is balanced. Is it not balanced? Oh, it's not balanced. Wait, is it not? Oh, there's a 2 missing. There's a 2 missing. Now is it balanced? Yes, the equation does need to be balanced. It's just I didn't give you a balanced equation. I'm getting sloppy. Okay, is it balanced now? 2, 2, 6. Yeah, now it's balanced. Okay, so maybe my answer was right. Maybe my thing was right. Okay, let's go back. So yes, the equation does need to be balanced. It should be a 2 there. Do know if we give you a balanced equation, it is explicit. We've checked all of them. It's just no one checks my work when I write these things. So I can be wrong. So let's see if this is right now. Let's try again. 0.08124 times 2 divided by 3 times 1.122.55. No, I'm still wrong. Okay, it's 6.6 now. 6.6, 6.7. Yeah, there we go. I'm sorry, guys. Okay, let's hope that 6 goes a little bit better here. All right. Okay, finally, some things without calculations. Yeah, I didn't give you a balanced equation in that one. Sorry about that. It must have like disappeared when I copy and pasted things. All right. Okay, so question 6. So this kind of reviews some concepts about gases and how they behave depending on, their identity or temperature. So one way that chemists and scientists compare gas samples is by calculating their RMS speed. Their RMS speed is a useful speed for us to compare because you can calculate RMS speed. RMS stands for root mean squared. It's directly related, related to the mass of your sample and its temperature. So the equation for this, are you given RMS speed equation? 3 RT over molar mass. Are you given that? Yes. Okay, fantastic. So this is how you calculate RMS speed. A couple caveats. See that there's an R here. This R, even though we're working with gases, it is not the same R that we are using in PivNert. This R is 8.314 joules. Oh, I always forget. I think it's mole. No, joules, mole Kelvin. I think that's the unit within there. All right. So this is a different R. It's actually the same R as the R gas law constant, but it's just in a different unit, so it's a different value. So do make sure if you're actually calculating the RMS speed here, you're using this 8.314 number instead. Temperature needs to be in Kelvin, as always. Molar mass, though, because of the unit of joule, it's a kilogram meter squared per second squared. Molar mass of your sample needs to be in the unit of kilogram per mole if you actually want to calculate an RMS speed for a specific sample at a certain temperature. So you can do that. You can figure out, okay, what is the RMS speed of argon at room temperature or something, and you can get that speed of that specific sample. And you'll see, just based upon this equation, you can see a lot of relationships that we can answer within here. We see RMS speed of your sample will increase if temperature increases, all right? Because temperature's in the numerator. If this number gets bigger for the same sample, then the speed goes up, right? Just based upon mass. Or if you change your sample, like if we're comparing argon to a lighter element like neon, I think that's what we're looking at here. Neon's a lot lighter. We will have a smaller number in the numerator. So if the denominator, if we go from argon to neon at the same temperature, the mass gets smaller, then RMS speed will increase as well. So you can see a lot of trends in the equation. So, you don't have to, I guess, memorize them per se, as long as you can inspect the equation and see, okay, what happens when we change mass? What happens when we change temperature? It all is based upon that RMS speed. Oh, I have it right there. Yeah, within there. So which of the gases possesses a faster RMS speed at room temperature? So again, if you inspect the equation we have here, neon will be faster because it is lighter. It has a smaller molar mass. And again, I dictate it's at room temperature, meaning that when we compare speeds of two different samples, we're comparing them at the same temperature. What that does is keeps the numerator constant, and all we're changing is the denominator. All right, so at which temperature will oxygen possess a faster RMS speed? So again, we're inspecting this equation. We're looking at oxygen. We don't have to calculate anything. You can, if you want, and prove it to yourself that oxygen will be moving on average faster at a higher temperature. All right, which gas will have a faster effusion rate? Effusion rate is related to essentially how fast it is going. So RMS speed. So effusion rate is, so that's if we develop a pinhole on the side of your container. And so anytime your a particle, your gas sample hits the container on that pinhole, it will effuse or escape from the container. So that's essentially what effusion rate is. So we'll see the rate of effusion. So gases will effuse faster if they're moving faster. So this question C is similar to A. Neon moves faster, so it has a faster effusion rate. And that is also given by Graham's law as well, where if you compare the rates of effusion of two gases, they're proportional to the square root of the molar masses of those two gases. So it's A over B for the rates, but then B over A for the molar masses. And you can see that in the key. All right. If we keep going here, which of these gases will deviate from the ideal behavior most at high pressures? So this is kind of inspecting our van der Waals equation. So it's, our kind of our Pivnert equation with some sprinkles put in there. So we have our pressure term, and we add our A term, n squared over v squared. Are you given this equation? I'm pretty sure you are. If there's a question about the van der Waals equation, it's given to you. And then the volume term minus NB, the B term within that equation. So this is essentially the ideal gas law, but just some adjustments within it to account for some of the assumptions we make in kinetic molecular theory. So the A term relates to attractions of the actual gas particles to one another. The B term takes into account the size of your particles. So and then the nRT part of Pivnert stays the exact same. So we have an adjustment on pressure. We have an adjustment on volume within there. So B related to size, A related to attractions of the particles themselves. So here, I'm asking which gas will deviate the most from at high pressures. So the idea here is let's inspect A and B. These terms I'm basically asking which of these substances are these adjustments, the largest. So this is slightly related to chapter 11, where we inspected intermolecular forces. Argon and neon are both atoms. So they're not polar, they don't exhibit hydrogen bonding or dipole-dipole. Really, they just have London dispersion forces. So I'm going to assume both of them have really small A values, both of them. But what is different is the B value. B value relates to size. Argon is bigger. So argon's going to have a larger B value. So this idea here for D is that argon will deviate more at high pressures because it's larger. That the ideal gas law, it follows kinetic molecular theory, and one of the tenets within that theory is that gases don't the actual gas particles occupy a negligible amount of space, meaning that when we say PV equals nRT, we assume that the volume is the volume of the container. And that's usually true for gases because gases, they're very they're not very dense. They're super light. The particles are far away from one another. But what happens at high pressure is you're shoving a bunch of particles in a small space. And so then the size of the particles actually matter, and the volume that those particles can actually move around is slightly less than typical. And so argon will deviate more because it's bigger. They just take up more space. So the volume amount, the space that they have to move around is a lot smaller within there. Okay, so that's D. So that's inspecting this equation. All right, and the last one here, E, which gas possesses a greater density at STP? And so this is kind of again, a density equals gram amount over liter amount. And so we use the same strategy here where the liter amount, we're assuming 1 mole of gas within there. And so since we're at STP, the liter amount is going to be 22.4. But it doesn't matter because both of these gases will have the same volume at STP, but what's different is the gram amount. So basically this question, what you infer from it, it's which is the heavier gas. And so it's going to be argon because argon has the higher molar mass. All right, so this is just like that other question we did. Argon, if you assume 1 mole, the gram amount is going to be bigger for that, for the numerator part there. Okay, so that is chapter 10. Okay, so we'll just keep going. Chapter 11, number 7 has to do with intermolecular forces. So with gases, intermolecular forces aren't super important unless we're talking about real gases, and the A term goes within there. But within the condensed phases like liquids and solids, intermolecular forces super important because that's what dictates the properties that we see. So within what we see here, we want to see, okay, which of these substances has the higher normal boiling point? So which of these samples boil at the higher temperature? So recognize that boiling is going from a liquid to a gas. So we're going from a condensed phase to gases. So when we boil something, we break all of the intermolecular forces. So the trends that we see here as intermolecular forces increases, we'll see an increase in boiling point temperature. Other relationships we also see, there's typically an increase of viscosity and what's the other one? Surface tension. When intermolecular forces of your sample increases, but vapor pressure of your sample actually decreases as you increase intermolecular forces. So all of these things relate to one another. And so we're just looking at the intermolecular forces present in these different pairs of substances. The question is there a difference between normal boiling point and just regular boiling point? So normal boiling point means when does a sample boil? When the external pressure equals 1 atm. So basically a sample will boil when its vapor pressure equals the external pressure. So I like to say, I feel like we all know that water boils at 212 Fahrenheit, 100 degrees Celsius, but that's only on Earth. Actually only on Earth at sea level is when water boils at 100 degrees Celsius. Water boils at 100 degrees Celsius because that is the temperature that's required to make the vapor pressure equal 760 torr, or 1 atm, because that's what's equal to the pressure, the external pressure, 1 atm on Earth. So if we went somewhere that had less pressure, then it would actually be easier to boil water, like on top of a mountain, like in Denver. There's high altitude baking instructions because water doesn't boil at 100 degrees Celsius. It's slightly less because there's less pressure there. So not sure what you mean by just regular boiling point. The temperature at which a sample boils is always the temperature at which your sample exerts the pressure, the external pressure on it. When we're on Earth, it's usually 1 atm. That's why, like when you look at recipes and stuff and boil water, that we can be consistent there, because we know mostly on Earth that water will boil at 100 degrees Celsius, but that's not true everywhere. That if you go like how a pressure cooker works, you're boiling water under higher pressure, so actually the temperature of water is a lot higher when it's boiling within there. So that's essentially why substances boil, is that their vapor pressure has to equal the external pressure. Okay, so it will change if the external pressure is a little bit different. Okay, so hopefully that answers that question. Okay, so we want to look at these substances, all right, and figure out which one has the higher boiling point. So this question is basically asking, okay, which one has the higher intermolecular forces present? So do recall all of the intermolecular forces in order of increasing strength. The weakest one is London dispersion, then it's dipole-dipole, then it's hydrogen bonding, and then ion dipole. But that's only, ion dipole is only important for ionic substances that are dissolved in water. So, and you can see on my strategy for IMFs, how you go about this. First, I usually look for is the compound polar or nonpolar? Because if a compound's nonpolar, like Br2, London dispersion force is the only force that's there. And that tends to be a very weak intermolecular force. So ICL here, so iodine monochloride, is going to have the higher boiling point because it is polar and it exhibits dipole-dipole attractions, that they're like little magnets in the liquid form that are attracted to one another. While diatomic bromine, it's nonpolar, and only temporary dipoles are created to keep that sample together. So ICL will have the higher boiling point because you need more energy to separate those molecules, because they're like little magnets attracted towards one another. So that's B. A, looking at these two compounds, I see some like weird things on the end here, like NH2. So I know that these compounds are polar because we have, highly electronegative atoms like nitrogen within here. So this nitrogen attached to a hydrogen, this can undergo hydrogen bonding. All right, that group, that amine group. Once you get to organic chemistry, you'll learn about some of these functional groups. So that group can actually hydrogen bond, and it is basically a stronger dipole-dipole. So it's our third one that we learn about that is slightly more, has more strength than dipole-dipole. There's more attraction there. Comparing it to the other substance, there's actually two different amine groups. So there's two sources of hydrogen bonding there. So to me, I see that this compound, the second one, will have a higher boiling point temperature, because this molecule, when there's a bunch of them all together in a beaker in the condensed phase, that each molecule can actually grab two other molecules and hydrogen bond, keeping it together. So it's going to be harder to boil. So there's two hydrogen bonding there, while this one only has one. So we're basically comparing the strongest intermolecular force. That's what's going to dictate the differences here. All right, and so this last one, pH3 and ASH3. So if you might have to draw the Lewis structures to figure out if this is polar or not. Both of these molecules, P and AS, are group 5A elements. So to me, I know that both of them will look like ammonia, where there is 3 bonds and 1 lone pair. So do we recall what shape that is? Just for fun. What shape is that? 3 bonds and 1 lone pair. Is it flat like this? Does it look flat? All right, and all those lines are hydrogens. What would this molecule, what shape would it be? Yeah, it would be trigonal pyramidal. So if we actually drew it, it would be the parent structure is a tetrahedron, but since one of those electron domains is a lone pair, we don't see that. And so what we're just looking at is the bonds that are made. So we see that it's like a triangle, it's a tetrahedron without the top. So it's a trigonal pyramidal. So both of these molecules exhibit dipoles, permanent dipoles. So both of them exhibit dipole-dipole. But then how else can we differentiate them? Well, their central atoms are different. So since both of them exhibit dipole-dipole, we can't really base it upon just that. Within here, AsH3 will have the higher boiling point because As is heavier. So since both of them have dipole-dipole, and we can't differentiate those, we kind of go to the next level. Can you go over ranking of IMF? It goes London dispersion, dipole-dipole, hydrogen bonding, ion dipole, and that's it. So just reread the notes. I'm sorry, we gotta keep going. All right, so the next one, question 8. Same type of thing where we're looking at pairs of substances here, and we're comparing their intermolecular forces, but this time it's asking for vapor pressure. Which one has the highest vapor pressure? So we have to kind of go back to these relationships. Vapor pressure, a sample will exhibit a high vapor pressure when it actually has low intermolecular forces. So I like to relate the idea of vapor pressure of a sample is like when like if we compare acetone and water, if you think about like what water smells like, and you're confused thinking water doesn't smell like anything, because that's true. Water doesn't smell like anything because it has a fairly low vapor pressure at room temperature. But if you smell acetone or nail polish remover, that has a very specific smell that we think of because acetone or nail polish remover exerts a very high vapor pressure at room temperature. So I associate high vapor pressures with things that are smelly. And so the reason we can smell those acetone molecules in our nose is because there's very, very small attractions in the sample of those particles that they easily escape to the gas phase to make it to our nose. So acetone has a very small vapor pressure, or sorry, very small amount of intermolecular forces, therefore a high vapor pressure. So this question is really asking which of these pairs has the lower IMFs. So all of these questions relate back to IMFs. So CCl4 and CBr4, both of those are non-polar compounds. They look like methane. They're perfect tetrahedron. So the sample that has smaller IMFs is going to be the lighter one. All right, so this is lighter, so lower IMFs. I know to look for the lighter one because both of them are non-polar. Both of them have London dispersion, and that's it. That's why we look at London dispersion because they're both nonpolar. All right, so the next one, we have this hydrocarbon and then another hydrocarbon with a chlorine on the end. So I know that this hydrocarbon is nonpolar, but the one with the chlorine on the end is polar because we have this new highly electronegative atom at the end. So it's the one that doesn't have dipole-dipole. So this one, the one with the chlorine on the end, will exhibit dipole-dipole because it has that uneven, that one electronegative atom on the one side. All right, and then C, this one's a little bit tricky. All right, H2o and H2s, both of these are bent, okay? So if you write out the Lewis structures, you'll see that on the central atom, there's, 2 bonds and 2 lone pairs, both of them are bent. But what's special about water is that it can hydrogen bond. It actually can do 2 hydrogen bonds, all right? Versus H2s cannot do hydrogen bonding. All right, so H2s will have the lower vapor pressure because it can't hydrogen bond. It can only do dipole-dipole, while water can do dipole-dipole and hydrogen bond. Doesn't that one have 2 H bonds though too? For B has none of these compounds cannot hydrogen bond. So recall the criteria for hydrogen bonding. You need a highly electronegative hydrogen atom. All right. And so how you get that is what you want to look for is an oxygen with at least one lone pair attached to a hydrogen. This is what makes a very, very highly electropositive hydrogen atom. The other one is a hydrogen attached to a nitrogen. And then the last one is a fluorine attached to a hydrogen. These are the only groups that can hydrogen bond. So S attached to a hydrogen, that cannot, even though there's a lone pair there, it cannot hydrogen bond. It's not one of the 3 that we look for. These are the only ones that can hydrogen bond. And so the note here is that there needs to be a lone pair on the electronegative atom. So I always show the example of ammonium, this compound, right? Ammonium, NH4 plus. So this whole thing is positively charged. So if you look at this at it like a really quick glance, you might be like, oh yeah, that can hydrogen bond. There's a nitrogen attached to a hydrogen that's electropositive. That hydrogen's electropositive, but there's no lone pair on nitrogen. So this actually cannot, ammonium cannot hydrogen bond. There needs to be a lone pair present. All right, so hydrogen bond is really important in biology. That is, one of the strong intermolecular forces that hold together, our proteins, our DNA, hydrogen bonding, and we're huge water bags. So like water is interacting with a lot of substances in our body. So in order to dissolve them, typically compounds that are within our body have places where hydrogen bonding can occur so water can interact. Okay, so hopefully that clarifies it. So that's why H2s cannot hydrogen bond, even though it looks just like water. It's just sulfur. That sulfur atom is not as electronegative as oxygen, so it can't hydrogen bond. Okay, all right. Which of these substances will exert the highest vapor pressure at their respective normal boiling points? I feel like I already talked about this earlier when I talked about Denver, boiling water in Denver, and like, I can't think right now, pressure cookers. So think about this question and write what you think the answer is in the chat. A, B, C, or D. You shouldn't have to do any calculations. Which one exerts the highest vapor pressure at their respective normal boiling point? I guess I should reword this question. Okay, I do not see any correct answers yet. Normal boiling point temperature. Okay, yeah, so I tricked you a little bit, right? We just talked about vapor pressure and I said that we see high vapor pressures with low IMF. So you guys, yeah, thought, oh yeah, ethane, that has, it's all nonpolar, it's the smallest molecule, it's going to have the highest vapor pressure, but that's only if we're comparing all of these samples at the same temperature. If we had all of these samples at room temperature on our desks and we smelled them, ethane would smell the worst. Actually, it would be a gas if it was sitting on our desk because it has such a high vapor pressure within there. But the idea here is that they're all at their normal boiling point temperatures. So remember what that means. When we have a substance that boils, P vape equals P external. What does normal boiling point mean? Normal dictates what pressure, what's the external pressure. Normal means that the external pressure is 1 atm. So when we are at the normal boiling point temperature for all of these samples, we have the vapor pressure of the sample is equal to 1 atm. So the answer is actually D. All of them have the same vapor pressure at their specific normal boiling point temperature. So for ethane, it's probably going to be a really low number. And for water and ethanol here, there'll be slightly higher numbers. But a sample will always boil when its vapor pressure is equal to the external pressure on it. So that is why the answer is D. I did not ask which one has the highest vapor pressure at a certain temperature, like at room temperature or something. So this question is asking something slightly different. And so the question is, does OH count for hydrogen bonding? These are the 3 criteria for hydrogen bonding. So there it is. So OH is included there. Okay, so any questions on that one? So 9 is a little bit tricky because we're thinking about vapor pressure, not our relationship within here, but based upon the definition of what boiling is. Okay. All right, what's the next one? Okay, is there other questions that we want to go over? Actually, let's isotopes and Bcaa tables. Okay, I want to just quickly do 11. Based upon, again, normal boiling point temperature again. So do recognize that normal means that the external pressure equals 1 atm. So we have a phase diagram of a substance. So if you're given phase diagrams on the exam, they'll be shown like this. So we have to recognize what these different regions mean. So these different regions, solid is usually here, gas is here, and liquid is here. Right, so do know that that's typically what that looks like. So I'm asking in this question, what is the boiling point, normal boiling point temperature for this specific substance? So the first idea is that we need to know that normal means that the external pressure is 1 atm. So we see that the y-axis is pressure. So 1 atm is right here. All right, just across there, because that's not a super straight line, but that's okay. And so our different phase transitions are these solid lines that we see. So we need to zone in on where is boiling. So when something boils, we are turning a liquid to a gas. So that's the transition that we want to look at. So if we think about, if we had this sample at 0 degrees Celsius or Kelvin, okay, so that doesn't, all right, so we were like 0 Kelvin and we start heating it up. It's going to be a solid for a while until we hit this temperature, I don't know, like 150 or something like that. Then it's going to melt and turn into a liquid. But then if we start heating up that liquid even more, then we will go to the liquid to gas transition, and that will happen at another temperature. So this question is specifically asking for this transition, liquid to gas, that's boiling. And so we just kind of think of, okay, what temperature is that? It's a little bit, it's more than halfway between 100 and 200. So I would say that the most reasonable number would be 170 Kelvin. All right. So this question, you know, if you don't know what normal means, that it means 1 atm within there. So if you didn't know that, then this question would be really difficult because you wouldn't know where to read this graph. Oh, look, there's my cat. She's right there. That's Bean. Say hi, Bean. She likes to sit on this chair with me. No one said hi. Okay, thank you. All right, meow, yes. Hopefully she heard that. Okay. All right, so melting point, so same idea here, more IMFs, higher melting point, all right. And some of these are ionic. Oh, actually, this is chapter 12, I guess. Let's do, yes, hi, Bean. I wonder if she'll sit with me. Okay, I want to do 12 because I think this is a good question. It kind of ties in both chapter 11 and 12, so don't get confused. So normal boiling point. And so remember, normal means external pressure of 1 atm, but melting point within here. So we're turning liquids, we're turning solids to liquids. And so within chapter 12, our solids chapter, our last one, even though, you know, we pretty much spent like one lecture day on it, predicting the melting points of ionic compounds, pretty straightforward. It is exactly the same trend we see in lattice energy, that we see an increase in melting point temperature when lattice energy increases. So if we recall, lattice energy is related to our potential energy equation, where we compare the charges of the ions that are present and their sizes. So if you know how to do lattice energy, you can predict melting points as well. Higher magnitude of lattice energy, higher melting point for ionic substances. But if we look at these, not all of them are ionic. Only strontium oxide is ionic. So we have +2, -2. Lithium fluoride is +1, -1. Lithium bromide is +1, -1. So we have these other two substances thrown in there, but don't let that confuse you. When we melt substances, we're turning solids to liquids. So we're still breaking some intermolecular forces. CH4 only has London dispersion present, while methanol here has hydrogen bonding. So we'll see that methanol will have the lowest melting point. It's going to melt first because there's just not as many forces holding it together. And then next up will be methanol because it has some intermolecular forces there. So within our solids argument here, ionic substances are going to have much higher melting points than molecular compounds, right? So you would consider both of these to be molecular. They're going to have much lower melting points within here. So the lowest melting point is going to be methane. Next up will be methanol. And then with these three, we just compare lattice energies. So I think lithium bromide, because bromine is larger than fluorine, will be next. Then it's lithium fluoride. It has a larger lattice energy than lithium bromide. So this is review of chapter 8, I think, 8, when we talked about lattice energy. So next up will be 4, and then strontium oxide will have the highest melting point within there. But I think the confusing thing is we threw in some molecular compounds there too. But remember, molecular solids have very low melting points compared to ionic substances. Okay, that's why a lot of gases that we see at room temperature, they're molecular compounds. All right, okay, let's do 13 too. Okay, so we talked about 4 different solids, different types of solids: metallic, ionic, covalent network, and molecular solids. So there's, I think, very defining characteristics for each of them and how we can identify them based upon description. So here I have a description. We have a solid, a soft white solid, and it's highly insulating. When it's added to water, it dissolves and the resulting solution does not conduct electricity. What substance is it? Why don't we throw it up in the chat? Why don't we throw it up in the chat? A, B, C, D, E. Soft. The solid is insulating. When we add it to water, it dissolves, but the solution does not conduct electricity. What do we think it is? A. I also think it's A. So hopefully you see some defining characteristics here. One is that it's soft. All right, so soft solids are typically molecular solids. A lot of the gemstones that we see are either ionic or like aluminum oxide and its relatives, like sapphire and ruby, are ionic solids or covalent network solids. So that's diamond. Metals, metallic solids, they have very defining characteristics. Those I know in the metallic solids, they are in their solid phase highly conductive. So I know that this substance can't be a metallic solid. So the only thing it can be is a molecular solid within there. And so kind of another reinforcing factor here is that the solution does not conduct electricity. So something like glucose or something, or sucrose, soft, solid, when you dissolve it in water, it does not conduct electricity because it's a non-electrolyte. So that's kind of back to chapter 4 also within there. So B is not one of the types of solids that we talked about. Also, let's pretend it was a weak electrolyte. If it was a weak electrolyte, then the solution would conduct, wouldn't it? So I feel like you should kind of be able to eliminate that one. Substance is an ionic solid. It can't be that one either, because if it was an ionic solid, the solution would also conduct, because ions would separate when it dissolves in water, and there would be free ions and it would conduct electricity. The substance is metallic solid. It can't be that one, because the solid would actually conduct electricity as well. And it's not E, because we actually can identify it. All right. So the idea here, what my kind of defining features for these different types of solids are. Okay, so weak electrolyte is not one that we talked about. Molecular solids typically have low melting points. All right, I think that's a defining feature. Also, they're oftentimes described as soft. Ionic solids, the solids do not conduct electricity, but the solutions do. So salt, NaCl, like if you had just like a piece of salt solid and you like put electrodes on it, it would not conduct electricity, because those ions are stuck in place. But once you put salt in water and those ions dissolve, then the solution with water does conduct electricity. But so the idea here is, but solution, or when we think about salt, aqueous, does conduct. Metallic solids, the solids do conduct. All right. And then the one that isn't shown here, I should have included it, but we have covalent network solids. Covalent network. Okay, covalent network. They do not conduct, no conductivity. And they're typically very hard, and they have very high melting points. So yeah, they're typically very hard, high melting points. Other defining features, metals are typically very malleable also, and that's due to the delocalization of metallic bonding here allows, metal atoms, those atoms to like move across one another without breaking within there. All right. So metals can be strong, but not brittle. Ionic solids are strong, but they are typically brittle, like salt, like they'll shear off one another, because you're essentially breaking across like ionic bonds within there. So, but metallic solids, you typically, if you bend like a piece of metal, the atoms shift, but because those electron clouds are so delocalized, the atoms shift, but the substance actually doesn't break. Okay. All right. So okay, let's just do this one. Let's just finish all the new stuff. Okay, so 14, let's look at this unit cell. So this is how we can think about solids existing in 3 dimensions. So, when we talked about molecules, we drew Lewis structures. That's in 2 dimensions, but we had to bring it to 3D, thinking about electron geometry, molecular geometry. Same idea with ionic solids. When we think about like NaCl solid, we know that there's a sodium cation and a chloride anion. But that's not the whole story. We actually need to recognize that we're packing millions and billions of sodium cations and millions and billions of chloride anions all next to one another. So when we have ionic solids, or just solids in general, we need to make sure that we maximize attractions between oppositely charged particles and minimize repulsions between neighboring cations or neighboring anions from one another. So that's very important, and that is what dictates the kind of the ordering and the shape atoms adopt in 3 dimensions in their solid form. So here I give you the unit cell of some theoretical compound. It has its 2 different atoms, A and B. We want to figure out what is the chemical formula, or the formula unit, or also it can be called the empirical formula. All right, of this compound given this unit cell. And so the strategy here is we need to figure out, okay, how many pink atoms are inside the box, inside the unit cell? how many purple atoms are inside the unit cell. So we have to think about inside. So like the atoms that are on the faces of the unit cell, only half of an atom is actually inside this unit cell that's drawn. The other half of the atom is in a neighboring unit cell that's not drawn. So the whole strategy here is figure out how many atoms are inside the unit cell. So start with each color separately. So I'll do the easy one here, the purple one. So what is purple? A is the purple atom. So I asked myself, how many purple atoms are inside the unit cell? So those purple atoms are fully inside. So there's 4. I see that there's 4 atoms in there. There's 4 A atoms, 4 A atoms. Do you see that? That those purple atoms are completely inside the unit cell. Okay. The pink ones are a little bit more tricky. B is pink. Okay. I think that's pink. So note of the different places that these pink atoms are put in. So let's just do the faces first, because I mentioned those already. So if we have an atom that's on a face, only half of the atom is actually inside the unit cell. So let's count how many atoms are on the faces of this cube. There's 1, 2, 3, 4, 5, 6. So if you remember, like how many sides of a dice, there's 6 sides on a dice. So that kind of makes sense here. There would be one atom on each face. So since there's 6 atoms on the face of this unit cell, and each atom, only half of it is inside, there are 3 atoms total just coming from the faces. But we didn't account for all of the atoms just yet. Now we have to do the corners. So I see that there are 8 atoms on the corner. Okay, on the corner. And so if we have an atom on the corner, that only accounts for 1/8 of an atom. And that's just due to where its placement is, that we have an atom that's straddling 8 different unit cells. So this one unit cell only has 1/8 of an atom. So if we add those 2 up, we see that there's a total of 4 B atoms inside the unit cell. All right, so if there's 4 B atoms, inside and 4 A atoms inside the unit cell, is the formula A4B4? Is that the formula? A4B4? Is that the empirical formula or the formula unit? No, it's not. We don't, if those atoms were sodium and chlorine, would you write Na4Cl4? Like, does that make sense? I hope you recognize that doesn't make sense. That's not, as chemists, we don't typically write formula that way, especially when it's an ionic structure like this. Yes, very good. It's AB is the formula unit that you would like write when trying to communicate with someone, that we simplify it to the simplest ratio. So it would just be AB within there. All right, so that's the first part. But then the question is, how many formula units are inside one unit cell? So we pretty much already answered it. I already know there's 4 A and 4 B atoms. We got the formula unit, or the empirical formula, as AB. So whatever number that we reduced it to, the reason it's A4B4 is because there's actually 4 formula units, or 4 AB formula units inside this one unit cell. So there's 4 of them within there. There's like 4 different pairs within that unit cell. And it's upon the like simplification that we did there. Okay, so we're done with new stuff. So what question we wanted to do? We want to do Bcaa. I don't even know if I have a isotope question. I don't even have an isotope question on there. So sorry. If you have my overview sheets, I have a bunch of isotope questions on my, I think, what is that, chapter 2 overview sheet. Just look at that. There's a bunch of them there. So let's do a Bcaa table. Everyone's favorite. Let's do 24. I like 24 because I think it's a Bcaa table, and it's the same equation every time. That's what I like about it. Okay. Ew, EW. Are you saying ew, or are you asking for something? Okay. So yeah, let's do 24. Let's consider this reaction. So I give you, let's make sure that it's balanced. I'm pretty sure that it's balanced. All right. So this double displacement reaction where we form a solid, silver chloride. So I give you a gram amount of the reactant, silver nitrate, and 15 grams of barium chloride. And we want to figure out what's how many grams of silver chloride is produced. So this isn't a Bcaa table. It's just a limiting reactant question. All right. So your strategy here is to take the two amounts that are given, so silver nitrate, and figure out, okay, if all of the silver nitrate reacts, how much silver chloride is produced? If all of the barium chloride reacts, how much silver chloride is produced, and you just pick the smaller amount. So we start with just one at a time. You have to do two separate lines. Like for me personally, I can't just look at these numbers and know which one's limiting. I actually have to calculate it and recognize this is a balanced chemical formula. So we need to be in mole amounts for these different substances. So we have 10.0 grams of AgNO3. We want to convert that to moles. So 169.9 moles, or sorry, grams over 1 mole of silver nitrate. And now we're in moles, so we can use the ratios that are given, but it's just 2 to 2. So 2 moles of silver chloride. All right, and then if we use the molar mass of silver chloride, AgCl, 143.3 grams equals, if all of the silver nitrate reacts, we get 8.43 grams of silver chloride. All right, so I'm not done yet. That might not be my answer. We have to do the same thing for barium chloride. So this time we're starting with 15 grams of barium chloride. Use the molar mass of barium chloride, so 208.2 grams over 1 mole of barium chloride, so BaCl2. Now this is where we do stoichiometry, so it's the same thing that we've been doing this whole year, and the same stuff that we did in chapter 10 when thinking about gases. The ratio is 1 mole of barium chloride and 2 moles of silver chloride. And then we do the 143.3 grams again, 1 mole. And so if you put that in your calculator and double check, you get that 20.6 grams of silver chloride is produced if all of the barium chloride reacts. So that means we pick the lesser amount, meaning that silver nitrate will run out first. So silver nitrate is limiting, that if we actually did this reaction and added gram amounts of everything, that we would actually only make 8.43 grams of silver chloride because silver nitrate is limiting. So that means barium chloride is the excess reactant in this case. All right, and so a little side question, what are the spectator ions in this double displacement reaction? So if we inspect here, all of these substances in the reactants are all of the substances in the reactants are strong electrolytes. They're ionic and they're aqueous. Silver chloride is a solid, so this does not break up. So my idea, and so barium nitrate on the end here is also a strong electrolyte. So I see barium is 2+ on both sides. So barium is actually a spectator ion, and so is nitrate. So barium and nitrate are both spectator ions in this example. All right, so that one's kind of like a chapter 3 type of question. 25 is the same reaction. So we're going to use the same balanced equation, but this time we're working in terms of molarity. But really, it doesn't change that much. We still kind of use the same ideas here. we need to be working in mole amounts to figure out, okay, what's the limiting reactant? How much product do we make? So we're using the same equation as above, but this time we're working with a certain volume and concentration of silver nitrate, a certain volume and concentration of barium chloride. So recognize that molarity, what that means. 1.0 molarity means that 1.0 moles of silver nitrate are in 1 liter of solution. So since we have 1 liter of solution, that means that there is 1 mole of silver nitrate present. And it's the same thing with barium chloride. Since it's 1 liter, 1 molarity, there is 1 mole of barium chloride present. So in this question 25, we want to know, okay, how many grams of silver chloride is produced again with this reaction, but also what is the concentration of the remaining chloride ions after this reaction is complete. So this second part of the question here requires a Bcaa table, because we want to know what's left over after the fact. And it's a lot easier if we kind of recognize what is going on completely in this reaction. All right. So I will do a Bcaa table to kind of answer this whole question. So I'm going to just copy this equation down here so I can do a Bcaa table. So the whole idea of a Bcaa table is that we need to be in the unit of moles of everything. B means before. So we just name what is in the reaction before anything happens. We have 1 mole of silver nitrate and 1 mole of barium chloride, but we have no products. So kind of just looking at this, if we have 1 mole of each, which one's going to run out first? I like to think of it as like, okay, you have 2 slices of bread plus 1 slice of cheese gives you a sandwich. If you have equal amounts of both bread and cheese, which one's going to run out first? You consume twice as much bread as you do cheese. So silver nitrate is going to run out first. Silver nitrate is the limiting reactant. So if it's limiting, that means we consume it all. Right? So if we consume a whole mole of silver nitrate, because based on stoichiometry, the change line is always based upon stoichiometry. Since we consume 1 mole of silver nitrate, that means we only consume half a mole of barium chloride. So same idea with stoichiometry. If we consume 1 mole of silver nitrate, because it's a 2-to-2 ratio for silver chloride, we gain a whole mole of silver chloride. And then the last thing here, this change line, again, all based upon stoichiometry. This is a 2-to-1 ratio. So we gain half a mole of barium nitrate within there. So the change line, you are just using your limiting reactant and using the stoichiometric ratios to get these different changes where since we're going towards products, we're gaining products and we're consuming reactants. And now it's just adding. So we consume all our silver nitrate. We should have 0.5 moles of chloride, barium chloride left. We have a mole of silver chloride, and we have half a mole of barium nitrate within there. So our answer for how much silver nitrate do we make a mole's worth. And so what's the molar mass? 143.3 grams. That's how much silver chloride we make. So that's the first part of the question. The second part, it's asking, okay, how much chloride ion is present afterwards? So that means we have to look at the after line and identify, okay, where are chloride ions present? We don't look at silver chloride because those chloride ions are tied up in the solid. We're just looking at the solution because we want the concentration of chloride ion. So we want to know what's the concentration of chloride ion in solution. So in solution afterwards, the only source of chloride is barium chloride. We have 0.5 moles of barium chloride present in the solution. But for every mole of barium chloride, there's actually 2 moles of chloride because of the 2 subscript there. So for every 1 barium chloride, there are 2 chloride ions. So we'll just have to multiply that number by 2. So there's actually 1 mole of chloride ions present. And then we just divide by, to get concentration, we divide by the total volume. And since we kind of, if you look back at the question, we took a liter of solution and added it to another liter of solution. So we're going to divide by 2 liters in this case, because that's the total volume within there. So the concentration of chloride afterwards is 0.5 molarity. I'm not sure about Sig Figs. I probably need 1 more. It's probably 2 Sig Figs of chloride present after the reaction is done. All right, so that is a Bcaa table. So there's a lot of ways to do this. In this specific question, I'm giving you a molarity amount and volume amount to fill out your before line. You know, I could have simply, you know, you can do the same idea here. You know, if you start with these gram amounts, you can also fill out a Bcaa table and see how that works out as well. It's just the before line will be created through mole amounts given by masses and molar masses. So the whole idea of Bcaa works for solution chemistry, for chapter 3 stuff. It works for gases as well. The whole idea is that within your Bcaa table, they have to be in mole amounts. Okay, what's the next one? The next one. Okay. Let's just do this one too, just because it's the same idea, using the same equation. Okay. How many milliliters of this concentration of silver nitrate is required to completely react with this volume and concentration of barium chloride? So we are given barium chloride and we want to know how much silver nitrate do we need. So this does not require a full Bcaa table. We can just go from one substance to another. We don't need to know the whole picture. We just need to know, okay, you know, 2 moles of silver nitrate are required to react with 1 mole of barium chloride. I know if I get a mole amount of barium chloride, I can figure out how much silver nitrate I need. So the big idea with molarity, and it's commonly misunderstood. Molarity is a concentration. That big M means, molarity means moles of your solute over liters of solution. So I always like to rewrite those molarity values into an equality that tells me exactly what it's relating. So what 0.035 molarity means is that there's 0.035 moles of silver nitrate in 1 liter of solution. Same thing for barium chloride. So 0.045 moles of barium chloride equals 1 liter of solution. So these 2 equalities will help me set up my dimensional analysis to answer this question. So I'll start with this volume amount. So 50 milliliters of that barium chloride solution. I want to get that into liters real quick, right? So now that I'm in liters of barium chloride, I can use the molarity of barium chloride. And again, that M doesn't tell you how the units work out. But if you rewrite it this way, you can see that I need to put the 0.0545 mole amount and the liter amount on top. So we're essentially dividing by molarity. I don't like to memorize, okay, I need to like divide, multiply by molarity to get the thing that I want. I just inspect the units and, you know, make sure I get what I want within there. So I see that, oh, nope, this is wrong. It needs to be the other way. So I'm in the, sorry, unit of liters. So liters has to go on the bottom. See, my units didn't work out. Liters goes on the bottom, 0.45 moles goes on the top. Hopefully you raised an eyebrow at me, but you just can't, you didn't type as fast as I realized it. So there, now it's set up where the liter amounts actually cancel. And then we have a mole of barium chloride on top. This isn't our answer. We need to get to moles of silver nitrate. So this is where we use stoichiometry. So 1 mole of barium chloride on top, 2 moles of silver nitrate up top. But we don't want a mole amount of silver nitrate. We want a volume amount. And so this is where we now will use the molarity of silver nitrate within here. So I will define, so it's 0.035 moles of silver nitrate on the bottom. 1 liter of solution up top. But then we need that to be in milliliters, then just one more times 1,000 to get that into milliliters. And so that would be our answer. And so I think the answer is 129 milliliters of silver nitrate. All right. So there you go. This question is no different than some of the other, reactant conversions we've done previously. When it's solution chemistry like this, recognize that molarity means moles over liters, where you can rewrite the unit of concentration into an equality like this. That kind of just makes a little bit more sense when setting it up in dimensional analysis. Do not use M1V1 equals M2V2. You will be wrong. M1V1 equals M2V2 only works for dilution calculations. Sometimes it works for neutralization reactions or reactions like this, but only when it's a 1-to-1 ratio. I implore you, only use M1V1 equals M2V2 when you're actually doing a dilution question. This is not a dilution. This is actually a chemical reaction. So if you did M1V1 equals M2V2, you would be wrong. You'd be off by a factor of 2, because what that does, it ignores stoichiometry. So doing this, just like we've always done within stoichiometry, works out that way. Okay, so someone asked me to do 33. So I will do 33. Okay. 33. So we have a tin atom that has 50 electrons. Electrons in the blank subshell will experience the highest effective nuclear charge. All right, so tin, SN, has 50 protons. Is that right? Is that 50 protons? Yes, that's 50 protons. So if you are a 35, that's selenium. It's okay. Tin has 50 protons in the nucleus. If you were looking at a tin atom, tin nucleus, you would see a plus 50 charge. If you were an electron in the N equals 1 subshell, 2 electrons, like if you write out its full electron configuration, 1s2, 2s2, etc. If you are in the front row seat looking into the nucleus, you would see the full charge of tin. This is essentially the idea of what Z effective is. Effective nuclear charge is what an electron sees after screening is taken into account. So Z effective equals Z minus S. So Z in this case for all of these electrons, because we're on a tin atom, is 50. But what changes is the shielding. So inner electrons have very small shieldings because there are no other electrons standing between the nucleus and that electron. So N equals 1 electrons actually have a shielding of 0, while as you go further out, like if we draw N equals 2, that looks bad. Okay, so this is my N equals 2 subshell. There's 8 electrons there. If I'm sitting in the second row looking in, these 2 electrons, remember, they're negatively charged. They're actually shielding the full charge of the 50 plus within there. So the shielding of an N equals 2 electron is going to be 2. So an N equals 2 electron is seeing less of the full charge of the nucleus. So the whole idea here, you don't actually have to calculate Z effective within here. I just recognize that you'll see high effective nuclear charge when there is a small shielding, or when your electron is closest to the nucleus. So I think the answer here is D, because 3s electrons only have 1s electrons and N equals 2 electrons shielding it, while like 5 N equals 5 electrons have 1, 2, 3, and 4. Like it has 4 rows of electrons in front of the full charge of the nucleus. So I like to think about it in terms of like seeding, like if you're at a concert looking at the stage, it's all the people in front of you, the electrons in front of you that are kind of reducing your experience of what's going on the stage. So the closer you are, the more fun that you're having, and the more, I guess, closer the full charge of the nucleus in the stage that you're seeing. Okay, go over 41 and 42. Sure. Okay. 41. Okay. A carbon atom with a triple bond must be what hybridization? Okay. So carbon, right? There's carbon. We have a triple bond. So take a step back and think, okay, carbon always forms how many bonds? How many bonds? Carbon always forms how many bonds in order to satisfy its octet rule. So just right now, this carbon, if you kind of calculate its octet, it only has 6 electrons. Yes, so it's 4. Carbon always forms 4 bonds in some capacity. It could be all 4 single bonds. It could be 2 double bonds. It could be a single bond or 2 single bonds and a double bond. But carbon always needs 4 bonds, right? In order to have a satisfied octet, there's 2 electrons in each of those bonds. 8 electrons total. Carbon has a satisfied octet within there. So there, I drew a carbon atom with a triple bond, and I needed one more electron here, or sorry, one more bond to complete its octet. So this idea, carbon has to be what hybridization? The idea of hybridization, how we determine the hybridization of an atom, is we look at that atom and we count how many electron domains are around that atom, and that will tell me how many atomic orbitals I need to hybridize to give that hybridization within valence bond theory to hybridize. All right, so if you count the electron domains around that carbon atom, how many electron domains are on that carbon atom? Please tell me, or please tell everybody. How many electron domains? Yes, there's only 2. So that triple bond only counts as 1 electron domain. So since we have 2 electron domains, we need to combine 2 atomic orbitals. So the idea is, okay, which ones do you need to include? You just count left to right. So we need to include 1 s, and then the second one's going to be a p orbital. So that means a carbon atom is sp hybridized here. Carbon, when there's a triple bond, there has to be sp hybridized. So the idea is we didn't touch these other p orbitals. Those are the orbitals that are involved in the pi bonds in the carbon atom. So one of these hybridized sp orbitals will, one of them will make the single bond. The other one will make the first component of a triple bond, which is sigma, and then the other 2 components are pi. That's what's coming from these unhybridized p orbitals. So if I redraw this, what a hybridized sp carbon would look like this. All right, where these are unhybridized p orbitals, the 2 that I didn't touch over here. So that's what hybridization looks like. And so these 2 hybrid orbitals are involved in the sigma bonds in the compound, and then these 2 are involved in the pi. So if I just kind of redraw this, like this electron is going to form that sigma bond. This electron is going to form that sigma bond, and then these 2 pi or unhybridized p orbitals are involved in the 2 other components of that triple bond. So carbon with a triple bond has to be sp hybridized in order for this to occur. All right, yes. So 42. Yeah, this one's a tough one. So which of these following interactions result in a sigma bond along the internuclear axis? So sigma bonds are head-on overlaps. There's a couple of ways that we can do it. Sigma bonds interactions, head-on overlap is like this, where we have 2 atomic orbitals and they come together via the internuclear axis and they come closer and closer together. All right, and then you have overlap like this. So the overlap of these orbitals is what creates a sigma bond. So we see how this interaction is similar to like 2 different p orbitals overlapping like this. Same interaction. Or we can talk about hybrid orbitals that look like this. All right, this could be like an sp3 and like an sp3 carbon, see how all of these interactions look exactly the same? Okay, those are sigma bonds. Or we could have something like this. See how this looks the same? Okay, that looks like crap. See, there's an s orbital and a p orbital. All of these have this head-on overlap. All right, like this. I always go like this: sigma, pi. A pi bond, pi overlap is like this. See how this overlaps? So pi interactions are always between unhybridized p orbitals. So this is a p interaction. All right, so it's a little different. So here, like something like that. Although my p orbitals are badly drawn, something like that. So it's a little bit different. See how the overlap is kind of above and below the internuclear axis when we have two unhybridized p orbitals. So the whole idea here is, okay, let's draw these atomic orbitals and see, do we make this interaction? So this first one is actually this first picture, right, where we have two different s orbitals coming together. So this one is a sigma bond. An example would be like diatomic, like hydrogen, like two hydrogen atoms coming together, combining their 1s orbitals. sp3 and sp3. So recognize that that's what this would look like, all right? Where like two carbon atoms in a chain connecting, if they're both sp3 hybridized, that this type of end-to-end overlap creates sigma interactions, all right? py and py. So I defined the internuclear axis as the z-axis. So this is the z-axis. So if we draw py orbitals, they're going to be along a different axis. So it's the same idea here that you know, if we kind of bring these two orbitals together, is this a pi is this a sigma interaction? No, it's actually a pi interaction. So this one is incorrect. Oops. py is not, B is correct. py is not a sigma bond. It's actually a pi bond. If we wanted to rewrite this so it was a sigma bond, it would have to be pz plus pz. All right, two pz orbitals, you know, if this is the internuclear act. Oh, that looks awful. Something that looks like that. Overlapping like this. See how they all look the same? All right, an s and a pz. So again, there's an s orbital, there's my pz along the internuclear axis. So I'm just going to bring that together. And I ask myself, does that look like a sigma bond? Yeah, that looks like a sigma bond. See how they all look the same? So yes, s and a pz is correct. All right, this one's a little bit tricky, py and pz. So so I already have pz drawn there. Let me draw py. py would look like this. Does this look like any interaction that we've talked about this year? Right here. Do you see me moving it? Does this look like anything that we've talked about this year? I hope you can recognize that this doesn't look like anything. That this interaction does not exist. It actually does not create any stabilization at all. So this is no interaction at all, that there's nothing going on there. So E is not correct either, that this actually creates no type of bonding interaction at all. And so the last one, sp3, so a hybrid orbital and a 1s orbital. So that would look kind of something like this one, but we replace one of those bonds, or sorry, one of those lobes with an s orbital instead. So s, sp3, and we see that, yes, this would result in a sigma bond like that. All right. So that one's definitely tricky. All right. And recognizing there's lots of different ways for orbitals to combine, but only some of them result in interactions that we care about. So for example, this one, pz and py, there's no interaction there. So there would be no bonding stabilization. There's no MO, molecular orbital, that results from that combination, because it doesn't give us any stabilization. What about px and py and px? Okay, px is good. All right, so so this was py and py. So if I drew px and px, okay, let me try to do my 3 dimensions. px is on, I guess, like in and out of the paper, so it would be more like flat. All right, so this is px. All right, so What type of interaction does that look like if I kind of bring those two things together? This, does that look like one that we talked about before? Yes, this would be a pi interaction. Very good. Yes, pi interaction. So it's the exact same as py. And the detail here is that py and px are not along the internuclear axis, but they do give rise to interactions, pi interactions specifically. And so you also asked about px and py. So it's the same idea. Like if we just kind of think about them in different geometries, if this is px and this is py, they are in different orientations. Again, does this result in a bonding type of interaction we've talked about this year? No, we haven't. So this actually creates nothing. It does nothing. So by that logic, would px and pz wouldn't interact either? You tell me. You tell me. Yes. Yes. Okay. Other question. I have 2 minutes. What other questions? Throw out a number. Throw out a number. 35. Okay. Oh, I can't do this in 2 minutes. Okay. So which of these molecules does not, okay. So in 35 and 34, you have to draw the Lewis structures. You have to draw the Lewis structures. Sum up polarity. No, you can't. You have to draw the Lewis structures. So of all 4 of these molecules, you have to draw the Lewis structures. So you have to follow the 6 steps. You have to then predict the electron and molecular geometries and determine whether the dipoles cancel out in 3-dimensional space. So in theory, you are summing up their vectors, they're bond dipole vectors, but in 3 dimensions. So we can have polar bonds, but if they are pointed 180 degrees away from one another, they actually cancel out in 3 dimensions. And so that would be a nonpolar molecule. So I think an example is Xenon Difluoride here. So xenon, if you actually draw this out, you have fluoride ions, and then you have, I think, 3 lone pairs. So this actually makes a linear molecule on a parent structure. I'm pretty sure. Yes. On a trigonal bipyramid. So there's 3 lone pairs, and those lone pairs will preferentially take the equatorial position. And so the fluorine atoms are actually 180 degrees from one another. And so those bond dipoles actually cancel in 3 dimensions. So this is a completely nonpolar molecule. So the steps are draw the Lewis structure, predict the geometry, and then inspect the central atom for bond dipoles within there. So I think the answer for the only polar molecules will be PCl3 because it looks like ammonia. All right, there's 1 lone pair, and TEF4. I think there's 1 lone pair on there, 1 lone pair on TEF4. Right. And then within obeying the octet rule for these 4, again, you have to draw the Lewis structure and inspect the central atom and just count, is there 8 or not? And so I think these 2 don't obey the octet rule. All right, so I'm done. Thanks for joining me, guys. I will post the video here soon. Have a great evening.